Hello everyone, in this lecture we will be solving 1981 IMO problem number 3. Here is a view of this problem. Determine the maximum value of m square plus n square where m and n are integers in the following range, satisfying the following equation. Probably we can start by testing a few cases. For instance, let's consider what happens if say m is equal to 1, because this is the least number we can pick, right? So in that case we would get n squared minus 1 times n minus 1 squared is equal to 1, which implies n squared minus n minus 1 is equal to plus or minus 1. And finally, I can split this into two cases. The first case is n squared minus n minus 1 is equal to negative 1, and the second case, n squared minus n minus 1 is equal to positive 1. In the first case, the minus 1s will cancel out, and factoring out the n will give us n is equal to 0 or n is equal to 1. Obviously n is equal to 0 is not admissible, so therefore we have the value for n. Alternatively, here we would get n squared minus n minus 2 is equal to 0, and this would nicely factorize as n minus 2 times n plus 1 is equal to 0. Finally, we would get n is equal to 2 or n is equal to negative 1. Again, negative 1 is outside the range, and we have the corresponding value of n. So from now on, let's call a pair of positive integers in this range 1 up to 1989 as admissible, mn admissible if m and n are in the following range 1 up to 1981, and they satisfy the given equation, n squared minus mn minus m squared is equal to 1. For that reason, for instance, in our particular case, some 1 would be an admissible pair under this case work, or we can also have mn would be 1 2 is another admissible pair. So far we have two solutions, and the largest of these is 1 2. So far we have just one candidate, but I doubt that would be the answer, because we have only tested one case, m is equal to 1. So therefore, for the rest of the discussion, let's assume that m is strictly greater than 1. And in fact, I will do the following. Let me make a change of notation. So let's instead of calling it mn, I'll call it n1. Why not? n1 n2 admissible, if again we pick n1 and n2 from the desired range, and also n1 and n2 satisfy n1 n2 minus n2 squared is equal to 1. So therefore all I did is change the notation just a little bit. Instead of calling it mn, I just called it n1 n2. And now, as we said earlier, for the rest of the discussion I will just assume that in this particular case n2 is strictly greater than 1. So therefore we can now investigate what will happen to this expression. We can simply work it out. So we can just take the square root of both sides, factor out the n1 here. We would get n1 minus n2, and then moving the n sub 2 squared onto the right hand side, that would give us n sub 2 squared plus or minus 1, because we took the square root of both sides. But then that's interesting because Right, because yeah, so obviously the right hand side is strictly greater than 0 because n2 is strictly greater than 1. So regardless of the sign here, we have something larger than 0. n1 is obviously greater than 0, so it must be the case that n1 is strictly greater than n2 as well. So when this is the case, then n1 would be definitely greater than n2. So as a result, this gives us an idea on how things might be working out. For instance, if I consider this as n sub 3, so does everyone agree on n1 and 2 being an admissible pair, right? So now consider this. I'll make the following definition. So let's set n3 equals n1 minus n2. Recall n1 is strictly greater than n2, and this inspires me to consider it as n3. If I substitute this into this expression, I would get the following. In fact, I can even substitute it directly right here. So okay, so the way I will do it is the following. So if this would imply that n1 is simply equal to n2 plus n3, so therefore substitute for n1 in this expression, in the original given expression, the following. So as a result, we would get, so this implies that n2 plus n sub 3 squared minus n sub 2 plus n sub 3 times n sub 2 minus n sub 2 squared is equal to, well, squared, I guess, right? So squared is equal to 1. As a result, this would imply, now the rest is just bashing out the algebra. So let me do it. Plus n2 n3 plus n sub 3 squared minus, we would get n sub 2 squared minus n sub 2 n sub 3 minus n sub 2 squared is equal to 1. Now finally, these two expressions would remove each other, so all I'm left is n sub 3 squared, and these two will also simplify, plus n2 and 3 minus n sub 2 squared is equal to 1. And now at this point I realize the similarity of the two expressions, except that there's a plus sign here which is not nice, but luckily we are inside the square, so therefore I can just multiply the things inside the parentheses with a -1 and it won't affect anything. So therefore I can organize it this way, minus n sub 3 squared, and now this is exactly an implication. So this would imply that n, how did we define it? I think, yeah, so n1 and 2 is admissible if the following holds. So therefore n2 and 3 is an admissible pair, is admissible. So that would solve the equation. But then that's pretty interesting, because now we have a new expression which is admissible, and in the case and if n sub 3 is strictly greater than 1, then as we did early on in our analysis, when right here, so then we can keep moving, right? So that would imply, like, if we keep track of the signs like we got here, that would imply that n2 is strictly greater than n3. But then if that's the case, let n sub 4 be simply equal to n sub 2 minus n sub 3, and it's by just following the same argumentation like this one, we would get that this implies, and so in this case we will just simply realize that n3 and 4 is also admissible, meaning also solves the equation at hand. And we will keep continuing doing this until, so we have a chain of numbers. Basically n1 is strictly greater than n2, remember here, and then n2 is strictly greater than n3, and so on. So this is strictly greater than. That chain will eventually stop. But when? Well, that chain will eventually stop when the difference between the two consecutive terms reduces to 1. So let's write that down. So eventually we will get where n sub I plus 1 is equal to n sub I minus n sub I minus 1. So each subsequent term is smaller than the previous one in this sequence, and finally it will terminate. The sequence terminates, well, it will eventually terminate, right? Because we have a positive sequence of positive integers, a sequence of positive integers, decreasing sequence of positive integers. We know that would have to eventually terminate, and this terminates exactly when n sub I is equal to 1. But then, if that's the case, we can work ourselves backwards, right? So if n sub I is equal to 1, that means that we have an admissible pair, the last admissible pair where last admissible pair, ordered pair is n sub I minus 1, 1, where n sub I is just a 1. And therefore, what we can do is we can work backwards. Work backwards. So therefore, from what we got at the beginning, we know that if m is equal to 1, then n, assuming that n is not equal to 1 as well, n would have to come out as 2. So in this particular example, so the last admissible ordered pair would have to be 2, 1. But then we can further work backwards. So what is ni minus 2, right? So what is n sub I minus 2? But then the recursion applies, right? So obviously we can find out the value of n sub I minus 2 by simply looking at n sub I, which is simply n sub I minus 1 minus n sub I minus 2. But n sub I is just 1. N sub I minus 1 is just 2 minus n sub I minus 2, which implies n sub I minus 2 is simply equal to 2 minus 1, which is equal to 1, which is absurd. So I messed up again. Working backwards, I just realized that I did another silly mistake here. It's really n sub I minus 1 minus n sub I, because the sequence is a decreasing sequence, so I should switch these two. Minus 1 minus n sub I, but luckily it doesn't affect my solution, so this is correct. The only part that it affects is this. Switch the numbers here. So let me redo this part quickly. So that would be n sub I minus 2 minus n sub I minus 1. N sub I minus 2 minus n sub I minus 1 is just a 2, implying that n sub I minus 2 is equal to 1 plus 2, which is 3. But then I just realized that, hey, I can just simplify this thing. So I can just move things to the other side, especially this guy. So therefore I get n sub I plus n sub I plus 1, giving me the previous term. But wait, this description reminds me of nothing but the Fibonacci sequence, right? I can work myself backwards. So therefore, if well, starting with 1, 2, we have 1, 2, then we got a 3, and then the next term would be a 5, an 8, a 13. What do I mean by that? So I mean that this guy is n sub I, and then we have n sub I minus 1, and so on, right? So this is greater than n sub I minus 2, which we just found here, and so on, n sub I minus 3, and so on. This one's n sub I minus 4, and we can keep going like this. So where do we stop? Well, the problem made it clear to us that the admissible range is from 1 through 1981. So let's keep adding the numbers, the Fibonacci sequence, until we reach 1981. And so we can go as follows. So therefore, let me carefully add the numbers. So we have a 21, 34, 55, and then 987, and then finally 1597. Ooh, the next one is 2400, 2500 something, which is not good because we have to stop at 1981. Remember, the sequence has to be less than 1981. So as a result, the last two, so all these things in pairs work, right? So for instance, let me use a different color. So the pair 2-1 would work, but then 3-2 would work as well, 5-3 would work, 5-8, 8-13, 13-21, 21-34, and so on. All these pairs would work. Eventually, this is the largest in the given range that would work out. So therefore, the maximum value, so the maximum value of m squared plus n squared is simply equal to, for mn in the given range, is simply equal to 987 squared plus 1597 squared, and that solves the problem. So this is a really cool stuff. So we worked our way backwards because the whole process, this construction is reversible, and as such we were able to construct a sequence which essentially is the Fibonacci sequence, with the exception that it stops at a certain point. So it's not an infinite sequence, but it has to stop. So therefore, for example, once we finish the backward, so if you start with this pair, if this pair works, which it does, which means 1597 squared minus 987 times 1597 minus 987 squared is equal to 1, and you can check the algebra. Then the following pair, which is 610, 987, also works. Then 377, 610 works, and so on. This pair works, this pair works. Eventually the pairing will stop here. As I said again, we would be done. So that's a nice problem. So hope you enjoyed the video. I'm looking forward to see you guys in our next lecture.